Hello, everyone. We'll be talking about AI and optimization for energy, supply chains, and mobility. And I was asked before the presentation to talk a little bit about myself. So I was born in a small country in Europe, in Belgium, and that's where I was also educated. And I was part of the first computer science department there. And as part of my education, I took classes in linear programming, rough theory, traveling salesman problem, stochastic processes. And I always thought that these topics were really part of the computer science curriculum. So I was very surprised when I came to the US to see that they were not, and that there was this separation between operation research and computer science. I spent 22 years in a computer science department before leading a research group in optimization, a large research group in optimization in Australia. When I came back to the United States, I worked in industrial and system engineering departments, first at Michigan and now at Georgia Tech. And currently I'm the director of the NSF AI Institute for Advances in Optimization. And this is kind of a dream come true because now I can finally reconcile in one institute computer science and operation research. So what you're going to hear today is part of what we are trying to do as part of reconciling these two fields and doing things that cannot be done by either field independently. Let me start by talking about optimization, a technology that has seen incredible progress in the last couple of decades. Now, when we want to solve an optimization problem, we first write an optimization model. Then we take some input, we apply an optimization solver, and as output, we get an optimal solution to our original problem. It's kind of magical, and these days we can do this sometimes for optimization problems that have millions of decision variables. But one of the things that we have seen in the last couple of years is that the optimization problems we face have been growing in size. They also operate in much more volatile environments. And for this reason, sometimes the optimization solvers have become too slow. This happens, for instance, when we have real-time constraints. We have to deliver an optimal solution or a near-optimal solution within a specific time frame. It also happens when we have humans in the loop, and these humans have to make decisions at the speed of business. They cannot wait too long before making those decisions. So one of the things that we have been exploring is whether you could use machine learning model to address those challenges. So we may think of replacing the optimization model by a machine learning model, shifting a lot of the computational burden offline during training of the machine learning model. And then during operation, for instance, we can apply the machine learning model to the input and get an output in milliseconds. Now, the challenges that we face are the fact that many of the problems that we are interested in have very complex physical engineering and or business constraints. They come from different engineering disciplines. Now, in the language of AI, what we are trying to do is to solve a problem which is called empirical risk minimization under constraints. And those are really, really challenging problems. But somehow we need to solve them because many of these engineering applications have very severe reliability requirements. They have to be deployed in critical infrastructures. Now, another challenge that we face is that many of these applications are of very large scale. We are sometimes talking about input sizes in the millions. We are sometimes talking about output size in the tens of thousands, let's say 25,000. And this is very different from what you typically see in machine learning for computer science, in computer vision or natural language processing. Now, as an optimizer, you also would like to have some performance guarantee. We would like to know how good the solution we are producing are, and typically that comes with providing some form of optimality gap. Now, to try to address those challenges, what we are exploring is this concept of optimization proxies. And an optimization proxy typically consists of two parts: a machine learning model and then a repair layer or a feasibility layer. And so what the machine learning part is doing is still the same thing. We are producing an approximation to the optimization algorithm. But now the repair layer is taking this approximation and transforming it into a feasible solution to the engineering applications that we are trying to solve. So let me illustrate that on a very simple two-dimensional example. So you see the optimization problem on the right here. You see the feasible region, and we're going to vary the objective function to show you interesting things. On the left-hand side, you see the machine learning model predicting the x and the y coordinates, the optimal solution. So one of the things that we're going to show you is the value of the optimal solution. The value of the machine learning algorithm, you can see here that the machine learning algorithm is producing a solution which is outside the feasible space. And you will also see the optimization proxy, which typically will overlap with the optimization solution. Now, if you look at the bottom part of this slide, you will see the optimality gap, and you will see the violations. Obviously, for the proxy, for the optimization proxies, the violations will be 0. So when I click, you're going to see the animation. Follow the machine learning solution, the proxy, and then the optimal solutions. And you're going to see some really interesting things. So you're going to see that the machine learning model typically produces an infeasible solution. You're going to see that very often the proxy and the optimal solutions are overlapping. You also can see that the optimality gap of the optimization proxies is very, very small in percentages. Now, what these optimization proxies are really doing is fusing AI and mathematical optimization to deliver outcomes that the two fields cannot achieve independently. And that's what this presentation is going to try to explain on real applications. This is the outline of the rest of the presentation. I will be showing you how we can apply the optimization proxies to energy system, supply chains, and mobility. And I will conclude by a couple of remarks. So let's dive into it and start with optimization proxies for energy system. Now, what you see on these slides is the optimization pipeline of an independent system operator in the United States. It's a sequence of optimization problems, most of which are mixed integer program, that makes two types of decision, commitment decision and dispatch decision. The commitment decisions are basically deciding which generators will be committed on or off for every hour of the day. The generation dispatch is deciding how much power every generator will provide every 5 minutes, as well as how much reserve they will provide. Now let's dive into this in a little bit more detail. An independent system operator at 10:30 every day is going to run what is called a day-ahead market, a day-ahead security constraint unit commitment. It's going to take the offer bid for load, consumption and generation, and it will be deciding which generators will be committed for every hour of the next day. It's a mixed integer program, which also takes into account all the constraints of the system, engineering and physical constraints of the system. Now, about 8 hours later, the independent system operator runs another optimization problem, another mixed integer program called the day-ahead FRAC. It's a reliability assessment or reliability commitment problem. It takes into account the offer bit, but also the forecast for the load, the wind, and the solar energy. And it will decide which additional generators need to be committed. Because now we don't only have the offer bit, but also a forecast of what can happen during the next day. Now, during the day of operation, every 5 minutes, the independent system operator is going to run what is called a LAC, a look-ahead commitment, which is again a reliability commitment. It's a mixed integer program that will again decide whether some additional generators need to be committed. And it takes again into consideration the offer bit, but an updated forecast for load, for wind, and solar energy. And then last but not least, because this is critical for the rest of the presentation, every 5 minutes, the independent system operator is running a real-time security constraint economic dispatch. It's a linear program that decides the dispatch targets of every generator, how much every generator will produce and how much will they provide as reserve. Now, this is obviously repeated every 5 minutes, every 15 minutes, and every day, and every week, and so on and so forth. Now, you have learned about the optimization pipeline of an independent system operator, and this is a massive success story for optimization. This optimization model, I run every day, I run every 5 minutes to keep the lights on. So what I want to do now is dive a little bit more into the SCED problem, a simplified version of the SCED problem, go over the constraints and the objective function. So the fundamental constraint that every power system has to satisfy is that the generation and the consumption have to be equal at all times. That's the power balance constraint that you see there. We'll talk about it again. We have also to satisfy all the reserve constraints, and in a system, you have typically many of them. And then we have to satisfy all the bound constraints for the generator, for the reserve, and also jointly, obviously, since a particular generator has to provide both electricity, power, and reserve. And finally, the last set of constraints that you see there are soft constraints. They are the thermal limits, the transmission line limits. They are soft, but they are heavily constraints in the objective function, which means that they are almost always satisfied. Now, this optimization problem is also minimizing cost, obviously. That's the goal of many of these optimization problems that I've been talking about. Now, one of the things that you may wonder is, why am I talking about these problems? Is optimization is actually really good at solving them. And the reason is that the system is becoming larger and increasingly volatile due to renewable energy, in particular wind and solar, which are much less predictable than a traditional generator. It's also due to uncertainty about the load. Because you have solar panels now on the roof of a lot of the customers, the load is much more difficult to predict as well. And finally, there is this electrification of the transportation system, which is happening right now, creating also a completely different load that system operators have been used to and have been used to predict. So one of the things that this independent system operator are interested in is to have better risk assessment tools. So one of the things they can do is to do a risk assessment the day ahead. They can start running a wide variety of simulation, trying to see what can happen to renewable energy, to load, and so on. One such simulation, one such Monte Carlo simulation, typically requires a large number of optimization algorithms, obviously, 96 mixed integer program, about 300 linear programs. And it basically requires 45 minutes. So if you have a high performance cluster, you can run a large number of them the day ahead and try to do this risk assessment and understand the risk inside your system. Now, if you want to do that in real time, this becomes more challenging. Obviously, the generators have been committed, but you still have to solve about 300 linear programs, which takes about 15 minutes. If you want to do this risk assessment for the next 5 minutes, it's extremely difficult to do. So what are we going to do? And so this is the place where these optimization proxies can be extremely valuable. You can look at every one of these optimization, every one of these security constraints, economic dispatch, and replace them by an optimization proxies. And now, instead of taking 15 minutes, you basically take 5 seconds for running an entire Monte Carlo simulation. So can you imagine now, we can run thousands of these simulations in real time and give a good assessment to the operator of the risk which is present inside the system. Now, what I have to tell you now is how we do this optimization proxy for the security constraints economic dispatch. And remember, these optimization proxies have two components, a machine learning component and then a repair component. And so what is happening inside the optimization proxy for the security constraint optimization dispatch is that we use a machine learning model to get an approximation to the solution. And then we have a repair layer which consists also of two components. A power balance layer which restores the power balance, and then a reserve layer which will be restoring the reserve constraints while keeping the power balance constraints satisfied. And that will give us a feasible solution that we can deploy. So let me give you the intuition on how we do these two repair layers. So this is the power balance, and I'm going to use a two-dimensional example again. But remember, in practice, we're going to solve this for energy systems that have about 10,000 buses or 30,000 buses. So the red line that you see there is the power balance constraint. So the dispatch has to be on that particular line. P in this particular case is the prediction of the machine learning model. And what we are trying to do is to bring it on this line. And so when the prediction is below the line, what we're going to do is scale up the generator. When it's above the line, we're going to scale them down. And you can do this by using a proportional response. So you can compute how much we have to scale, the percentage that we have to scale every generator, given the freedom that they have, and then how much we have to scale them down if we have too much power. And so the equations are shown here on the right-hand side. And one of the beautiful things that we'll talk about is how nice they are. You'll see that this is going to be extremely useful. So if we apply this proportional response, one of the things that we have now is that the power balance constraint is satisfied. And the next thing we have to do is to repair the reserve constraints. Now, to do this, the first thing we can notice is that we can project out the reserve variable and reason only on the dispatch variable. So this is what this theorem on the right is telling you, is that you essentially can find out if they are reserved that are feasible if the conditions that you see on the right is satisfied. So we only need to reason on the dispatch of the generator, the active power. Okay? And once again, what I'm going to show you is to illustrate what is really happening here in that layer in a graphical fashion. Okay, so look at the top figure there. So this is what we are predicting. We satisfied the power balance constraint, but this is the feasible region of the reserve constraints, and we are obviously outside. So we have to bring this particular prediction inside the feasible region of the reserve constraint while staying on the line representing the power balance. Now, the way we do this is by looking at two types of generators. Every generator can be classified in two types, depending on which constraints are tight. Now, this constraint here, which is tight, is the reserve constraint. So our generator has a reserve constraint, which is tight, but it has freedom on its generation. So in a sense, we can still satisfy the reserve constraint, but increase the active regeneration of the particular generator. So this is nice because we can step up the generator while keeping the same level of reserve. This one is interesting. So what we want to do is increase the reserve, but the only way to do this is by decreasing the power. That's the other type of generator. All right, so we're going to classify the generators that way. And now we can define the layers in the following way. We can find out which generators have an active reserve constraint, which generators have an active power constraints. We can start seeing what is the maximum increase and decrease in energy that they can sustain. And then we can try to do compute a proper ratio such that we have, again, a proportional response that we can apply. And this is what this reserve layer is going to be. So in both of these layers, what we are doing is applying a proportional response to different set of generators such that we can restore feasibility. Okay? Now, how are we going to train this? So at this particular point, what you see there is that we have an optimization proxy that we can apply. We can have a machine learning model, get an approximation, and then restore feasibility. And so we can apply that during operation, right? Use a machine learning model, get this approximation, restore feasibility. Okay? Now, what I want to tell you about is how we can train that machine learning model. And the traditional way to do this would be to say, okay, so I'm going to take this machine learning model and I'm going to train. I'm going to take all the inputs, and I have a huge database of them, and I'm going to train the output which are associated with every one of these inputs. And that's going to be giving me the targets that I want to meet inside the machine learning model training. And you can apply traditional, gradient descent, stochastic descents on this, and propagate back the loss function into the parameters of the neural network. But what I want to show you is that we can actually do better. We can do end-to-end training. What we can do is we can look at this proxy globally and then train every pieces of the optimization proxy jointly. Not only the machine learning model, the neural net, but also the power balance layers and the reserve layers. And if we do that, essentially during the training, we're going to be able to back-propagate from the output to the parameters of the neural net through the reserve and the power balance constraints. And obviously, we're going to do that for every one of the instances. And one of the beautiful things that we are doing here is that every time we train this particular model, we are generating feasible solution, not approximation. Every one of these feasible solutions, every one of the solutions that we are generated are feasible. They are inside the feasible region. All right? So why can we do this? We can do this because essentially every one of the layers that I've shown you, obviously in the the deep neural network, and also in the power balance and the reserve layers are differentiable. They essentially are differentiable almost everywhere, and you can compute subgradient everywhere. And this is extremely useful because now if you have your loss function, you can actually backpropagate to the layers of your neural network. Okay? Now, we can do that in two different ways. The traditional way to do that is to use supervised learning. So you start with your optimization model. You get a large number of instances. Every one of these instances consists of the input of the optimization model and then the optimal solution. And to do that, obviously, we have to have the solution to these n optimization models. Some of them may come from historical data. Other ones may be data that you have generate, we call that data augmentation, to actually have a set of optimal solution for every one of these input data. Now you're going to select an architecture, a neural network of a certain size with certain parameters that you want to train, and then you're going to train the model using a supervised loss function. And the loss function typically consists of two components. The first one is the supervised loss. You want to make sure that the prediction that you are generating using the machine learning model is as close as possible to the optimal solution. That's the loss that you see there in blue. And then you will have typically constraint penalties for the constraint that are violated. Now, one of the beautiful things that we have when we are training this machine end-to-end is that we are always feasible. So we don't need the constraint penalty. We don't need to use Lagrangian duality and other concepts that have been introduced in the context of machine learning as well. But we simply can focus on the supervised loss. How close are we when we are generating this feasible solution to the optimal solution? That's what we can do with supervised learning. Now I want to talk about something that is super interesting now. I want to talk about self-supervised learning. And this is something that I find really, really exciting. So instead of having instances where you have the input and the optimal solution, we are only going to look at the data set which has the input. So we are not going to require the optimal solution to all these optimization problems. We are just going to look at the input. Again, we are going to select a particular architecture which is parameterized, but now we are going to use what we call a self-supervised loss. And that self-supervised loss has two components again. It will have the original objective, the objective of the optimization problem. And then it will have the constraint penalties for the constraint that I violated. But again, when we are doing this end-to-end architecture with the feasibility restoration, we have no violation, we generate only feasible solution. So what we are really training the neural net and the repair layers together, what we are really training it with is the original objective function of the optimization model. And this is super exciting because you don't need any training of the optimization model, and you are really looking at the objective functions of the original optimization problem. Okay? So you avoid the training of all these instances optimization problems that you need to solve. And in the particular case of the SCED, this is how the optimization function would look like. It would be the cost of the dispatch as well as the soft constraint violations. This is the objective function that I've shown you before. This is the original objective function of the SCED. So let me talk a little bit about the results, and I'm going to show you a result for problems which are extremely large. These are some of the largest test cases that exist. You have a test case here with 30,000 buses, some with 13,000 buses. It's a part of the European network. This is the French system. So these are really realistic and large-scale test cases. What you see there is the training time, which is reasonable. It's about 40 minutes. What you also see, this is the supervised learning approach, this is the self-supervised learning approach, is that here we don't need in the self-supervised approach any training time. We don't need any time for solving the optimization instances, which is the case in the self-supervised learning, and those times are pretty substantial. So the supervised learning approach is spending a lot of time here solving the optimization problems before it can even do the training. And the self-supervised learning completely avoid that particular part. The second thing that I want to show you is the speed at which you can use this optimization proxy. So when you look at the optimization proxies, it takes about 10 milliseconds. And this includes the machine learning prediction, as well as the feasibility restoration using the power balance and the reserve layers. The last thing that I want to do is the value of this end-to-end learning. This is the optimality gap of the solutions by the self-supervised and the supervised learning approach. And you can see that for these very large instances, the optimality gap is smaller than 0.5%, which is kind of remarkable. It's actually better when the optimality gap is actually lower when you use self-supervised learning compared to when you use supervised learning. So these are, really exciting results in my opinion, because they provide the technology to do this real-time assessment that independent system operators are really interested in doing. Let me talk about the second part of this presentation, or the application of optimization proxies to supply chains. And we're going to talk about e-commerce. And as you know, e-commerce has really exploded during the pandemic and is still predicted to continue to increase, given the customer expectations for these kinds of services. And to sustain these kinds of e-commerce growth, you really need strong logistic capabilities. You need to reduce cost. You need to make sure that you improve sustainability, and all this while maintaining the service guarantee, the quality of service that the customers now are expecting from these kinds of services. Now, the challenges that we are facing when we look at the optimizations of these types of e-commerce logistic is the fact that these service networks are massive. They have hundreds, thousands of terminals. The daily shipment volume is about 10 million packages shipments. And there are a lot of fluctuation in these shipments, from one day to other, from one season to another. So it's a really challenging problem from an optimization standpoint, really, really challenging, even if you look at pieces of it. So this is a little bit, one of the problems that you face, and this is called load planning or load consolidation in e-commerce. And so what you see here, let's assume that we are trying to ship some shipment from Atlanta to Chicago. Typically what you will have in these types of network are primary and alternate routes. You want to send your shipment through this primary route, in this particular case, going through St. Louis. But there are also alternate routes that you can take if the primary route is too congested and if you want to consolidate your load in a better fashion. So you can go through Nashville or to Columbus, for instance. So as I was telling you, this primary and alternate path are kind of defined beforehand. They are kind of constraints. They define what you can do with your shipments. But then the real problem that you face is how you consolidate the shipment into loads. And loads here mean the number of trucks or type of vehicles. You try to minimize the cubic capacity for these vehicles that you are providing for serving all these shipments. And obviously, that's one of the things that you have to decide: how much of this load, how much of these trucks you have to provide, but also where the shipments are going, in which truck the shipments are going, because this is actually a critical decision for the e-commerce provider. So we can do this using a beautiful optimization model. This is the optimization model that we came up for in this particular area. I won't go into all the details, but I want to give you some snapshot that will be extremely useful for the optimization proxy. So the first thing is that obviously you have, again, a balance constraints. And in this particular case is whatever shipment is coming in has to go out. And so this is this balance constraint that you have to satisfy, flow balance constraints. The second constraint that you have is the capacity on the vehicles, on the trucks, on the load. And you have to make sure that the shipment that you put in a particular load, meet the capacity and don't exceed the capacity of that load. Now, there are two types of decision. The first one, the most important one, is how many loads do you need? So this is the Y variable. Remember that. The Y variables are going to be the load. And then you have the X variable, which are basically the flow decision. This shipment is going into that load, into that truck. So these are the two decisions that we have to take. Y for the load, X for the flow. Now, this optimization model brings very significant improvement in efficiency compared to the human planners. So it's really an interesting contribution to e-commerce to be able to solve these optimization problems and deploy them. But they have challenges, especially when you start moving to the largest facilities that these e-commerce providers, logistic providers have to operate. The MIP models are very difficult to solve, primarily because they have weak linear programming relaxation. But they have also another challenge, which is interesting from a practical standpoint, is that these optimization solvers have stability issue. And so what you see at the bottom is what happens to the optimal solution for some of these routes, primary or alternate routes, when you increase a little bit or decrease a little bit the cubic volume that you have to shift. And so you can see here that the number of trailers that you need for that particular route is varying, considerably. It's chaotic, right? So it increases and decreases as you vary the volume that you need to ship. And this is across many different parts of many destinations, many different parts of the facility. So again, what you have are two challenges here. The MIP are difficult to solve, and then they produce optimal solutions that are very different. And this is coming from the fact that you have a lot of symmetries in the solution space. There are multiple ways for consolidating this load. You can send 3 trucks across these 3 paths, or 3 trucks across 1 path, or 2 and 1, or 1 and 2. It can be completely different, and the optimization solver can return any of these particular solutions. So this is extremely confusing for a human planner. If you keep changing the solution that the human planner is seeing, she will probably not be very happy, and she will be confused by the system and not accepting the use of a particular optimization system that does that. So we have to face and find a way to solve these two challenges. So let's address the two of them in sequence. So the first one is addressing the stability issue. And this will allow us to actually address the other issue as a side effect. So we want to do a goal-directed optimization. And by that, I mean that the first thing we will do is to first minimize the trailer capacity. We are trying to find out how much, as few trucks as possible, as few trailers as possible that are needed for meeting the volume that we need to ship on a particular time. Once we have this optimal training capacity, what we are going to do is symmetry breaking. We are going to use the reference plan, because we always have a plan at some point. We are going to basically try to find an optimal solution which is as close as possible to that reference plan. So we do 2 optimizations, one for finding the minimum trailer capacity, and then another one which keep this minimum trailer capacity but break the symmetries to be as close as possible to the reference plan. So let me show you the model here. So this is really an addition to the models that you have already seen. It's a little bit different, obviously, but it's very, very similar. So what you see here is that what we are trying to do is to stay as close as possible to the reference plan. That's what you see inside the objective function. But what you see here at the bottom in this particular constraints is that you also want to implement the minimum capacity, the minimum volume capacity, trailer capacity that you need. So you maintain the optimality, but at the same time you try to minimize the distance compared to the reference plan. And by doing that, you hope that you will generate a stable solution. And these are the results. So you look at exactly what we have seen before. And you can see, the blue here, the blue is representing the capacity, the trailer, the number of trailers that you need for that particular route. And so in this particular, on the right-hand side, it's beautiful. It's like the same number for that particular variation of the volume. It's a little bit, oscillating here between 1 and 2 in the case of the left route. So once we have solved this, now we are in a position to say, I'm going to run this goal-oriented optimization such that I can solve these problems in real time. And so we are going to use a training and testing pipeline, which is a little bit different from what we used inside the energy system part of the talk. And the reason is that the feasibility restoration here is quite complicated, as you will see. So offline, what we're going to do is take some historical instance, augment them to have many, many more instances, solve them optimally, and then train this machine learning model. And then online, we are going to use the machine learning model to get an approximation of the solution and do feasibility restoration only then. So we don't do end-to-end learning and optimization here. And then we get the modification to the reference plan that is provided by this feasible solution. So what this pipeline is going to allow us to do is to find high quality feasible solution very, very efficiently, and they will be stable. So let's go into the detail of this, because the details are actually very, very interesting as well. So we had a lot of difficulties actually training the machine learning model initially. And so what we decided to do is to actually focus only on one part of the optimization model, the load decision. So we are here predicting the load and not the flow inside the machine learning model. So predicting the number of trailers for everyone traveling around every one of these paths, primary path, alternate paths, and so on. And then in the second step, in the feasibility restoration, we're going to correct these load decisions and at the same time find the flow decisions. So how, where are the shipments allocated? So once again, what we are doing here is really, really novel in the sense that we are not trying to predict all the decision variables on the machine learning model. We are predicting the one which are important such that we can do a really, really nice feasibility restoration. So let me tell you a little bit about the feasibility restoration. So we do that in two stages. The first stage is actually identifying the flow which has violations of the capacity constraints. Typically, this is solving a linear program to actually find that out. And then we have the second stage, which is the important stage. We solve a MIP model which will determine which additional equipment is necessary, because we can still do load consolidation during that feasibility restoration step. And so the model that we get is a MIP, and it's going to resemble, as you will see, the MIP model that we have seen before, but there will be some really, really interesting differences. So the first thing that you see is that what we are doing for all the capacities that have not been violated, we fix the load. So if we have a particular path where there is no violation, we fix that particular load. Now, for the other ones, we will use, that we have identified in the first stage. So we know that the capacity was violated. We know how much equipment we need to potentially fix it. We are actually will give those particular paths an opportunity to put more trailers. This is what you see with this XC and US variables and constant there. And obviously what we will do inside the objective function is trying to minimize the additional capacity, the additional trailers or load that we are adding to the prediction. So one of the interesting things when you solve this, when you actually look at what the prediction model is doing, is that 99% and sometimes 99.5% of the decisions, the load decisions, are actually correct. You don't need to change them. You can fix them. And so the MIP that you've just seen is a much, much smaller MIP compared to the original MIP that we were solving. And this is why this feasibility restoration, as you will see, will be able to be done in a very short amount of time. So again, what I'm telling you here is that the variable which are fixed and the variable which are not fixed, have a proportion which is 99% and then 1%. So it's a 2 orders of magnitude reduction in the size of this mixed integer program. And so these are the results that you can see. So on the right-hand side in blue, you see the time and the total variation compared to the base plan which is returned by the optimization proxy. So this optimization proxy now can be solved in about 2 seconds. And they have a variation which is around, total variation in cubic meters of, let's say 500 for the largest facilities available. Now, this is the goal-directed optimization. In about an hour, it has an order of magnitude larger difference compared to the base plan. Obviously, these two are optimal or near optimal for the proxy. And so you see a fundamental difference here between what the proxy can do and what the goal-directed optimization can do. If you implement a heuristic, you will see exactly the same kind of difference. So 2 orders of magnitude difference almost, and then also much larger time using a sophisticated greedy heuristic using linear program, for instance. So what these experimental results show you is that in this case of supply chain, once again, optimization proxies can let you do something that cannot be done by either optimization or machine learning independently. And this is a truly nice result for optimization proxy. So let me move now to the third application area and the applications of optimization proxies to mobility systems. And again, you will see in this particular context new features of optimization proxies that you have not seen in the previous 2 application domains. So the context here is real-time ride-sharing systems, and they can be part of larger systems like on-demand multimodal transit system, where they basically implement the on-demand part of the system, or they may be ride-sharing systems on their own, for instance, like Uber Pool. And so what we are doing is that given a set of shuttles and the willingness of customers to ride-share, what we want to do is minimize the expecting waiting times for every one of the customers, every one of them. So we provide guarantees of service. And we also want to avoid long waiting times for particular riders. So we want to minimize the expecting time, but we also want to provide guarantees that any individual riders is not going to wait too long. And we obviously want to meet all the constraints of this type of application, not violating the capacity of the vehicles and things like this. So this is a visualization of a system like that for New York City. What you see there, the little block there, the little rectangles are the demands, the request for services. The blue moving lines are vehicles that are moving with a particular customer or more inside the vehicles. And then the red moving lines are essentially vehicles moving towards a particular customer or a group of customers. And you can see how fast these customers are being served here. So the way we do this optimization is by optimizing over a rolling horizon. So we batch requests for about 30 seconds, then we optimize those requests the next 30 seconds, and at the same time we batch the next generation of requests, and then we optimize and batch and optimize and batch and keep repeating this. Now, how do we optimize? So we optimize using a very nice column generation algorithm. And so this is the kind of the master problem of this column generation algorithm. We are minimizing waiting time. We are making sure that we are covering all the riders that are making requests and making sure that every one of the vehicle is only driving exactly one route. We have a penalty actually for the customers that we are not able to serve at a particular point in time because we can't solve this problem optimally. It may happen that we cannot serve a particular customer. In this particular case, we associate a penalty, and this penalty is increasing exponentially such that we are sure that they will be served in a reasonable amount of time. And we capture obviously the riders that have not been served in a particular period of time very quickly. This is the kind of results that we get. We basically can serve every one of the riders with 2,000 vehicles and a waiting time of about 3.5 minutes. Now, New York City for serving these requests is about 12,000 vehicles. So this is a substantial reduction in vehicles here and a very, very small waiting time. So we were really, really excited by these results until I asked my students to actually visualize how much vehicle were busy, how busy the vehicles were and how idle they were. So the blue points that you see here this time are vehicles which are idle. And you can see a massive number of vehicles that are idle. And this is not because the system is not doing well. I mean, you saw the results. But this is because dispatching some of these vehicles here to, let's say Times Square is going to take a very long time, and you would increase the waiting time too long. So you basically make them come slowly and slowly and slowly towards where the demand is located. So this is a problem. This is a real problem because we are not maximizing the utility of these vehicles. So what are we going to do? So what we decided to do was to build a model predictive control on top of this optimization. So every 5 minutes, instead of every 30 seconds for the core dispatching algorithm, we have a relocation algorithm that decides, whether we should relocate vehicles and where. And so we, basically partition the entire city in zones, and we decide whether some vehicles have to be relocated to a particular zone. And to do that, you use obviously a mixed integer programs, which is really complicated. I won't go into all the details, but they decide, what every one of the vehicles are doing, whether you move them, to another location, another zone, and so on. And you have typically several types of constraints that you would expect, right? So the flow conservation on the request, the flow conservation on the vehicles, and the objective function minimize the number of unserved requests and the relocation. So we do that for over time, obviously, for a number of periods. But the problem becomes really, really challenging as you are increasing the number of periods. If you move beyond 30 minutes, go to an hour and so on, it becomes much more complex. So this MPC is very difficult to solve, especially for very long time horizon. But we have a lot of data about these particular problems, and the instances are very similar every 30 seconds, every 5 minutes, and so on. And we have a large amount of historical data. So the key point is, can we use optimization proxies? Can we use an algorithm which will predict, where to relocate the vehicles, and then make sure that these are feasible decisions? And the way we are going to do this is interesting on its own, because you don't have to, again, learn the entire optimization problem. The only thing that you really need to learn is the decision that you do in the first period, because that's the vehicle that you need to relocate now. The other ones, you don't care. I mean, in 5 minutes time, you will redo the optimization. Now, the problem is that these decisions are often very sparse, and therefore very difficult to learn. So what we do is that instead of actually predicting exactly the relocation that have to be done, what we are predicting is how much vehicles are relocating from a zone and how much we are relocating to a zone. So we are not predicting, origin-destination pair. We are predicting, hey, how many vehicles are leaving a zone, how many vehicles are coming to a zone as part of the relocation. And so the learning, again, is going to be a deep neural net, and then the repair is going to be a transportation problem, making sure that the vehicles that are leaving the zone actually go to a particular zone, and that we restore feasibility. And so the results here are pretty compelling, I can tell you. So what you see there is the deep neural net for approximating the model predictive control for 6 periods of time. You cannot do that in real time, but obviously the machine learning model will be able to do that in real time. What you can do in real time is essentially 2 periods of time. And what you see here in this particular result is that you get essentially the same waiting time. If you are doing this model predictive control, which cannot be done in real operation, right? And the deep learning model, they have essentially the same waiting time. They have the same relocation as well, and the same relocation time. So this machine learning model, this optimization proxy, can actually approximate the model predictive control algorithm with 6 periods extremely accurately. Now, can we do better than that? So the model predictive control now do 6 periods, maybe an hour, but this doesn't capture the long-term effect, right? So you are basically looking at a particular hour or a particular, 30 minutes at this particular point. But we have a simulator here. We can simulate everything. We can look at these trajectories of what the vehicles are doing. And therefore, you have the opportunity to do deep reinforcement learning here. You can actually use these trajectories to improve the MPC policy, which means improving the optimization proxies. And the key idea is exploring several actions around the optimal solutions or the near optimal solution recommended by the proxies, and then do policy gradient optimization. So you take the optimal solution, put some Gaussian noise around them. The state of your reinforcement learning is the demand and the supply over the next K period, and the reward is the total waiting time and the weighted relocation time. And you find a policy which is basically minimizing this expected reward with some discounted factor based on time. And when you look at the results here, this is really interesting. There is obviously no change for the waiting time in the short term. Because this is not what the reinforcement learning methodology is going to help you with. But what you can see is that it helps you actually relocate less. You look at the trajectories and you actually exploit the long-term effect and relocate some of the vehicles in a less greedy fashion. You can improve the relocation miles by about 10 to 15% by doing the reinforcement learning. So at this particular point, you have seen the use of optimization proxies for energy system, for supply chains and mobility. And I want to conclude. I want to tell you that these optimization proxies are a very exciting development. They fuse machine learning and optimization, and they produce high quality solutions extremely fast. And they can do things that optimization and machine learning independently cannot do on their own. So it's really the combination, this fusion of optimization and learning, which allow us to do to achieve some of these results. Now, there are key features that I want you to remember. We can do end-to-end learning. We can choose between self-supervised or supervised learning. Self-supervised learning having some benefits in some classes of application. Feasible restoration can be done in different ways. We can use optimization. We can use differentiable programming if the feasibility layers are differentiable. We can use also reinforcement learning on top of these optimization proxies. There are a lot of potential direction here. So this is essentially what I wanted to tell you today in this presentation. This idea of optimization proxies and the fact that they can do things that the two technology, machine learning and optimization, cannot achieve independently.